Second time in history, a man-made object has left our solar system. NASA is saying the Voyager 2 probe.
Voyager 2, one of humanity's most enduring space explorers, has once again captured the imagination of the scientific community with a discovery that defies long-held assumptions about the boundaries of our solar system. Launched in 1977, the spacecraft has been drifting farther from Earth for nearly 5 decades, transmitting data from regions of space never before explored by human instruments. Now, as it cruises through the outermost edge of the heliosphere and into interstellar space, Voyager 2 has detected something astonishing, something that was not predicted by any model or theory. It has uncovered an anomalous region at the boundary of the solar system, a place where fundamental rules of cosmic physics appear to shift, and where existing understanding of solar and interstellar dynamics falters. Before we start, hit the like and subscribe buttons for more exclusive news. As Voyager 2 crossed the heliopause, the boundary where the sun's solar wind is stopped by the interstellar medium, it sent back measurements that baffled scientists. The region was expected to be a turbulent, chaotic mixing zone of solar and interstellar particles. Instead, the spacecraft recorded an area that was surprisingly calm, eerily structured, and electrically charged in ways no one had ever imagined. Instead of a messy frontier between solar influence and the galaxy beyond, Voyager 2 revealed what seems to be a well-defined and orderly structure with uniform magnetic fields, directional particle flows, and an unexpected lack of turbulence. This was not just surprising, it was completely counter to all predictive models of the solar system's boundary. What made this discovery even more incredible was the presence of a previously unknown layer, a thin, dense, and sharply defined plasma wall beyond the heliopause. This plasma barrier had never been detected before and had no precedent in existing astrophysical theories. Voyager 2's plasma wave instrument detected a distinct change in density as it crossed this region, indicating a sheath of tightly packed ions that somehow maintained coherence even at the chaotic edge of the sun's domain. This dense wall appears to act almost like a shield, filtering and reshaping the influx of galactic cosmic rays in ways not seen before. The existence of this feature suggests that the heliopause is not a simple transition zone, but a dynamic and layered boundary with physical processes not yet fully understood. One of the most startling findings was related to the magnetic field. When Voyager 1 crossed the heliopause years earlier, it also recorded changes in magnetic field orientation. But Voyager 2, traveling along a different trajectory, found that the magnetic field lines outside the solar system were unexpectedly aligned with those inside, as if space itself had been somehow restructured to match the solar system's internal field. This symmetrical alignment goes against all expectations. The solar magnetic field and the interstellar magnetic field were thought to differ significantly in orientation and strength. Yet, Voyager 2's instruments showed a strange, almost mirror-like continuity in magnetic direction, as though some unknown mechanism was enforcing order across the boundary. This symmetry is not just a curiosity. It challenges foundational assumptions about magnetic reconnection, solar wind decay, and galactic field dynamics. It suggests that the edge of the solar system may be influenced by forces or interactions not yet understood by modern astrophysics. Perhaps a hitherto undiscovered physical principle governs the interaction between solar and interstellar magnetic fields. Some scientists have even speculated that this alignment hints at a form of cosmic architecture, a larger structure in the galaxy that guides or shapes magnetic flows on a scale far beyond the reach of the solar wind. Adding to the enigma is Voyager 2's detection of directional cosmic ray flux. Galactic cosmic rays are high-energy particles originating from outside the solar system, and they typically bombard the heliosphere from all directions. But as Voyager 2 exited the solar bubble, it recorded a pronounced asymmetry in these incoming particles. The cosmic rays seemed to be funneled or guided, arriving preferentially from specific vectors rather than a random scatter. This behavior implies the existence of a galactic-scale lensing or shielding mechanism, possibly related to the newly discovered plasma wall or some other structure extending far beyond the heliosphere. The implications of this are profound. If cosmic rays are being selectively directed or modulated at the boundary of the solar system, then Earth and the inner planets may be receiving only a filtered version of galactic radiation. This could dramatically alter our understanding of radiation exposure over geologic timescales and may even have implications for the evolution of life on Earth. It's conceivable that the heliopause acts not merely as a passive boundary, but as an active modulator of cosmic environments, protecting or exposing planets within it to varying degrees of energetic particle bombardment. Perhaps the most mind-bending aspect of Voyager 2's discovery is what it suggests about the true shape and structure of the heliosphere itself. For decades, it was assumed that the heliosphere resembled a comet-like tail stretching behind the solar system as it moved through the galaxy. But data from Voyager 2, combined with new simulations inspired by its findings, hint at a radically different form. Rather than a teardrop shape, the heliosphere might be more spherical or bubble-like, enveloped by a high-pressure shell where interstellar and solar forces collide in unexpected harmony. This reimagined heliosphere would imply a far more symmetrical and contained solar influence, again contradicting long-standing models and demanding a re-evaluation of our cosmic neighborhood's architecture. The very act of discovery here is almost philosophical in its scope. Voyager 2, a human-made object launched in an era before digital technology became commonplace, has traveled beyond the influence of our star and shown us that the universe is still full of surprises. It has pulled back a curtain on the workings of the interstellar frontier, exposing a boundary that is not merely a point of fading solar power, but a vibrant, active, and startlingly structured region. Every piece of data it sends challenges the narrative that space beyond our solar system is simply cold and empty. Instead, it hints at a stage of energetic interplay where cosmic forces sculpt environments that we are only beginning to understand. These findings have set off a cascade of theoretical re-examinations. Plasma physicists are grappling with how such a defined plasma wall could form and remain stable in such a volatile region. Magnetohydrodynamic simulations are being recalibrated to include magnetic field alignments and low turbulence boundaries. Cosmic ray experts are rethinking the pathways and shielding mechanisms of energetic particles on a galactic scale. The standard solar model, too, may need revision, not at its core, but at its limits. How the Sun interacts with the galaxy is no longer a question of distant academic interest. It now shapes how we think about the solar system's place in the cosmos. The discovery also suggests that the boundary between solar and interstellar space is not a fixed location, but a dynamic and responsive frontier. It breathes, shifts, and responds to both solar cycles and galactic conditions. Voyager 2 recorded subtle pulsations in particle density and magnetic strength that imply movement and change, even in this remote and seemingly static region. The heliopause may contract and expand, its position dictated by the strength of the solar wind, the pressure of the interstellar medium, and even the influence of unseen forces beyond our current capacity to detect. What's even more intriguing is the possibility that these unexpected structures and forces are not unique to our solar system. If our Sun creates such an elaborate and controlled boundary, it stands to reason that other stars may do the same. That opens the door to an entirely new field of comparative heliophysics, where astronomers might study the bubble boundaries of distant star systems using indirect observations or future interstellar probes. The cosmos could be dotted with structured stellar cocoons, each shaped by the interplay of solar and galactic physics, each creating its own unique environment for planets and potential life. Voyager 2's findings also raise questions about the navigational landscape of interstellar travel. For any future missions that seek to cross into the galactic neighborhood, whether robotic or someday crewed, the nature of this boundary is critical. Knowing that the heliopause is not just a vague transition but a structured zone with active shielding properties changes how spacecraft might be designed, how they might communicate, and how they might manage exposure to radiation. It becomes a kind of checkpoint, a barrier that must be understood and accounted for, not just crossed. Moreover, the discovery invigorates the search for dark plasma or exotic particle interactions. Some theorists have long speculated that there might be unknown forms of matter or energy that interact weakly with conventional particles, and the strange behavior at the heliopause might be a hint. The plasma wall, the magnetic alignment, and the cosmic ray filtering could all be evidence of interactions with such unknown forces. While this remains speculative, the mere fact that Voyager 2 encountered phenomena so far removed from theoretical predictions gives these fringe ideas new weight and urgency. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on Voyager 2's discovery? What do you expect it means? We want to hear from you. Thank you for watching, and see you next time.